Today we'll be discussing the differential, linear approximation, and the fundamental theorem of calculus. Now we'll visit the board where Justin will introduce the differential.
A pretty straightforward process is the differential. So if we're trying to find the differential in x is the change in x as it moves across the x-axis. Pretty straightforward. If we're looking at the differential in y, it's equal to the first derivative of the function x with respect to x.
Fascinating. Are there any actual uses for this? So using the definitions of differentials in x and y, we are able to do linear approximation. So first we have our function, which is f of x. Then, at a certain point on the graph, called x, we find the tangent line. So that is point x. Then, we take another separate point where we want to find the approximation, and call that x plus delta x. This point is the sum of your initial x plus your change in x, or the differential, which is delta x, as our definition is called. So then, once you have that, you want to find the difference in y from this point, which is y, to this point, which is the f of x plus delta x. The difference in between these 2 points is called delta y.
So we're going to use our definition of the linear approximation model to make an estimate. Our number that we're going to estimate is the cubed root of 63. So we're going to find the actual value of the function, the cubed root of 63 on our calculators, which ends up being 3.979. So we're going to make our equation the cubed root of x, where x equals 64. So we could also rewrite x as 1/3, which is going to come in handy later. Our formula that we're going to use is f of x plus dx, which is going to be equal to f of x plus the first derivative of x with respect to x. So to get 63, we're going to have to take 64 minus 1. So negative 1 is going to be our dx, or our change in x. Now over on this side of the equation, we have our f of 64 plus the first derivative of 64 times our dx, which we concluded was negative 1. Now we're going to make our linear approximation. So we're approximating the cubed root of 63. So here we have our equation f of x, which is the cubed root of 64, plus what we have here is the first derivative of x, which is 1/3 times x to the 3 halves, where x equals 64 in this case. And we're going to include our dx here, which is still negative 1. Now as we move down to simplify that, we get 4 plus 1 over 3 times 16 times negative 1. When we add that all up, we get 3 and 47/48. Now here if we put this into our calculator, we get 3.9792. As we showed earlier on our calculators, the cubed root of 63 is equal to 3.9791. In this case, our error is just 1/10,000th, which is pretty good.
And now to Donnie with our environmental awareness issue of the day.
Silly turtles. Rubber bands aren't belts.
So as you okay, we gotta go.
There's an earthquake at our last location, so we're changing spots. It's the fundamental theorem of calculus.
The fundamental theorem of calculus states that lowercase f is a continuous function defined on a closed interval a to b, and uppercase f is an antiderivative of lowercase f. Then the derivative of f of x dx from a to b equals the antiderivative of b minus the antiderivative of a. Can I just draw out a graph and explain it?
Yeah.
Say you have the function f of x. If you take the integral of the function f of x, this will give the total area beneath the graph from the interval a to b. If the function f of x equals x cubed minus 4x.
It's graphed here. We're taking it over the interval -2 to 2. So this area is shaded. We're trying to find the net area. Alright, so we're going to try to take the interval of the function f of x dx over the interval -2 to 2. So this is our function, which we got from up here. When we integrate this, we get 1/4 x to the 4th minus 2x squared over the interval -2 to 2. As you can see here, the equation is expanded, and after you do all the simple math in this part, you get down to 4 minus 8 minus the quantity 4 minus 8. And eventually, once you get down here, it's -4 plus 4, which equals 0. And if we go back to our graph, you can see that the negative area of the equation plus the positive area should equal 0, because they're equal on both sides of the graph. Alright, now say you wanted to take the gross area of this graph with the function x cubed minus 4x. In the last segment we did net area, which was the positive minus the negative, which ended up being 0. So say we wanted to take gross, which would be the absolute value of the negative area of the equation plus the positive. So as you can see here, we changed the limits from -2 to 0, which is the positive area, and then we're adding the negative area, the absolute value of it. So from 0 to 2 of the function f of x dx. As you can see in our nice new colored marker, over the limit -2 to 0, we're going to integrate the function x cubed minus 4x and then add the absolute value of the integrated function over the limit 0 to 2.
So these last two examples showed us how to find the net and gross area. It's important to remember that the net area is the total space in between the function and the x-axis, whereas the gross is found when we compute the absolute value of both the above and below the x-axis. Think of the gross area as taking this function and flipping it back over the x-axis. That would be like finding the absolute value and just computing this area. Using the fundamental theorem of calculus, we can find definite integrals. For example, take the integral of x squared minus 3x from the interval -2 to 0. So we write this out and find the integral, which becomes 1/3 x cubed minus 3 halves x squared over the interval -2 to 0. You're going to take your upper limit, 0, minus your lower limit, which is -2, and put these into the integration and then solve it out. So we end up with 0 minus 0 minus a -8/3 minus 6, and you're left with 8/3 and then a common denominator. So 8/3 plus 18/3 is equal to 26/3.
Thanks for joining us on this episode of Math Class. And if you'll excuse me, I've got to finish beating my high score in Phoenix.